All right, let's go ahead and get started. Woohoo! All right. It's great to see you all. Thank you all for coming. Again, feel free to make yourself as comfortable as you possibly can in this room. I apologize for the mix-up. I should have double-checked. I actually teach in this room regularly, so you think that if it said Longfellow G08, I would have figured out that it was the wrong building. So I'm sorry for those of you who had to walk back across the street. But let me first start by introducing myself and thanking you all for coming. So I'm Andrew Ho. I am a professor here. I teach measurement and statistics. I'm a psychometrician. Those of you who saw me this morning, what I usually say is that sounds more like an insult than a job title. Psychometrician means that I do work with psychological measures, and in particular I'm interested in educational testing and how to make educational testing better than it currently is. But I teach in our statistics sequence, which has a long history here in the School of Education, founded by Judy Singer and John Willett, who've written academic articles about how to teach statistics. So I came here and was like, oh, that's how it's supposed to be done. And I've tried to take the torch and continue to pass it on to future generations and teaching fellows and doctoral students. And so this course and variants of it now exists across the country. And what I'm here to do today is give you a little bit of a preview for those of you who might never take it. Right? So the target audience here is not those of you who are inclined towards the stat sequence, and actually more towards those of you who, again, are like, I don't know why I'm here. My friend dragged me. I really do not feel like I belong. And so this is like, if I had just like 10 things that I could give you from all that we teach throughout this year and beyond, what would those 10 things be? And so without further ado, because I've got a lot of slides, I want to jump right into it. So you can see the heads and the tails here, but I want to start with something really important. I think Dean Long Bridget said this morning, one of the most important things that we can do in orientation and throughout the first few weeks of school is say to ourselves, I belong, and say to each other that we belong, okay? And I think this is particularly important because this discipline of statistics, and in particular, I should say educational testing, has had a long and sad history of exclusion and excluding people from this practice. And I think this actually brings tears to my eyes, one of the more important cartoons I've seen in this, XKCD is just an incredible cartoon. So I just want to lay this out here from the beginning. This is what we fight against when we learn statistics. This is what we have to do sitting in this classroom and outside this classroom, right? When we learn math and statistics and quantitative methods, we have to fight back against like the buildup of pressure against, in particular, women and underrepresented minorities in this country and beyond when it comes to learning math and statistics. So I just want to lay this out here from the beginning that this is how it works. And this is you can see this here. Wow, you suck at math. Wow, girls suck at math. Right? And this is what we fight against when we sit in this room. And what we have to remember is constantly out there and this pressure that we have to push back against when we teach and learn statistics. And so I want to start with the message of outright inclusion. And I'm very, very glad that this course, and my predecessors I have to thank for this, have had a long history of inclusion. You can see it in the results, right? And the people who go on to teach, the people who go on to practice statistics, that they're diverse and from all different backgrounds and came thinking, I am not a numbers person, and left owning it. And I think that is the most important thing that I can leave you with today, is this feeling like I can be a numbers person, right? That is the most important thing I can leave you with. And so I want to start with a mantra. I want to start with not just the statistician's mantra, but the learner's mantra. And I want you to, this is what I hope you can say and then ultimately believe, like, I am not afraid to be wrong. I'm not afraid to be wrong. I came here today being open to being intimidated by these numbers, but I'm not afraid to be wrong. If I am wrong, it means I haven't learned it yet. Yet is that key word. That's that sort of growth mindset word, right? And again, not just that we can do it on our own. We have to help each other do it, right? Because that is what we're fighting against, okay? So what I want you to do is just start off by saying, like, introduce yourself to your neighbor. Say your name, your advisor, your program, and where you were this past summer. And then I want you to just sort of sneak in there this mantra and look your neighbor in the eyes and say, like, let me just affirm for myself that today, because we're going to be doing a little bit of participatory action here. I'm not afraid to be wrong. If I'm wrong, it means I haven't learned it yet. Make sure you say it. You have to say it. All right, so with that, let's all be wrong together and learn together, okay? So I want to jump right into this with the first thing I'd like you to leave with, right? I'd like you to be able to answer the question, what is statistics? Like when we say statistics, what is that fundamentally? And I want to start with a little bit of a presentation that shows like how what I think learning is. Learning is like seeing the world with new eyes, right? It's like a new kind of perception. When you look at the world, I want you to see it differently, right? That's what this entire year and hopefully this next hour and a half can be about, right? Can you leave here looking at the world in a little bit of a different way? So here's the question: what does randomness look like? And this comes from a great article that was published a few years back. So here what we have is World War II, a map of bombs that fell from German bombers in World War II in London. Right? And so you can go back to and imagine that if we have this map of bombs that fell across London, we might ask, was German bombing of London targets random or strategic? And you can imagine this is a pretty important question. Right? Did they have the ability to aim? And if they were aiming, where were they aiming? Right? And so the question is, do you see a pattern here? Right? Are they trying to hit the bridges? Are they aiming right over here? Are they aiming right over here? Are these clusters? Are they targeting things? Or is this random? And you can imagine, again, the way you'd set up your defenses, the way you try to protect your citizens would be very, very different if this were completely random and they had no ability to aim, or if this were systematic. You can see how important of a question this is. So let's push off on that question for a little while. Let's also address one of our colleagues, Steven Pinker, here at Harvard. Which one of these is random? The one on the left or the one on the right? Right? So which one of these feels more random to you? And again, remember the mantra, do not be afraid to be wrong. If you're wrong, it means you haven't learned it yet. All right? So what I want you to do is think about this a little bit. Which one looks more random to you? And then I want you to hold up one finger if you think this is the random one, and two fingers if you think this is the random one. These are what we call at MIT finger exercises, where it means everybody has to participate because you have to put up your hands. Do you think one is more random on the left, or two is more random on the right? This is really hard. Let me make sure everyone's got their hand raised. Okay, so the answer is one. But what I want to hear is someone argue, and I think there's a really good reason for thinking this, right? Why does two feel like it's more random? There's a perfectly reasonable, rational way to think about this. Yes?
The dots seem more evenly spaced.
The dots seem more evenly spaced, right? And these clumps look like there's a pattern. If you cross your eyes, do you see the 3D picture? You know those? Right, it looks like these were. Look at that clump. Look at that clump. Right? Look at that clump up there. Right? How could that have been random? Right? And so this is the question, right? It's the way we're seeing the world that hopefully will shift for those of you who picked 1 to 2. Now let me see if I can convince you. Here's another example, right? So here's student 1. Student 2 is again from Steven Pinker's book. This is student 1 who they said, okay, flip a bunch of coins and record your coin flips. Right? One of these students was cheating. It's like, flipping these coins just takes way, way too much time. She said she's just like putting down things that she thought looked random. Right? Which one of these students was cheating? Right? Which one of these is random? And which one of these is systematic, forced? Right? So which one is random? If you think this one is random, hold up 1. And you think this one is random, hold up 2. So again, now you're sort of switching your perception a little bit, right? You're like, oh, wait a second. Like maybe the clumps, right, are kind of what we expect, right? So this is where student 1 is the random one, and student 2 is like, I think I know what randomness looks like. It means we have this like even balance of heads and tails, right? And the fact is that clumps, these patterns, happen randomly. And yet we don't think of them as random. Right? We think there's something there, right? Because that's what our minds do. That's what we're trained to do. We're trained to see patterns in the noise, even when there's just noise. Wouldn't it be good if there was some rigorous set of tools and techniques that we could use to keep us from seeing patterns where there really aren't any? right? So again, this is the true random one. This is the true random. And you're like, wait, what? Look how many heads there are there. That just doesn't happen by chance, except of course, when you have this many coin flips, a lot of things that are unlikely happen, and it starts to become a little bit more unlikely that something unlikely won't happen. Should I say that again? Right, so let's do a little bit of a demo here. This might not completely convince you yet, but let's do a couple of demos, right? So here this is what Steven Pinker called glowworms and stars. So glowworms, so stars are what's on the left here. They sort of naturally clump. They're sort of randomly spread out throughout the sky. They're not really random, but that's okay. This is what sort of stars look like, that kind of randomness. And what do glowworms do? Glowworms need to eat in their dark caves, right? And so what they do is they spread out from each other. They actually put effort in to get away from each other, right? And so that's not random. They're like, no, we have to order ourselves so we each get food, otherwise I'll starve. Right? So that's what the glowworms do on the cave walls in the dark, right? And so what you can see here I'm going to simulate, right, what this looks like. So this is true randomness, and this is randomness that I've forced into being glowworm-like. Every dot is like in its own little square, right? And so what you can see is if you look at true randomness, right, there are these clumps that just happen. You're like, whoa, what does that spell? It's spelling a letter. It's like talking to me, right? So you're like, what is that? I mean, what are the chances of that coming out? And of course, this is totally random. And these like weird patterns that you see just start happening by chance with every little flip of the coin. So similarly, there's a great site called random.org, which I feel like should have more random things that aren't random. So here's flip again. Oops. And so I just flipped. Look at that. I should like buy a lottery ticket, right? Right? Look at all those tails all in a row, right? And so what I encourage you to do, and then you'll have all these slides and you can take a link at them. Look at all these tails; they're everywhere, right? And look at that; it's like a cool little design with all the tails. So this is again purely random, and yet we can't help it. We see these patterns where there are none. Right? And that is why we need something like the statistical tools we have to be able to tell, right? Because if you're trying to decide whether or not the bombings are strategic or random, you don't want to see patterns in the noise that aren't really there, because then you set up defenses and lose lives when you shouldn't. So there's actually even an FAQ at random.org. Right? Here's one of the FAQ. What if I don't think the die rolls or coin flips look very random? I really like this response. It's very gentle, right? Sometimes people email us to say that they feel the dice roller produces too many repeated numbers, right? That it's hard to roll 5 dice without getting 2 or more identical rolls, or the coin flipper produces too many heads or tails when used with several coins. Such concerns are great illustrations. I agree. Great illustrations of how difficult it is for humans, including me, right, to deal with randomness. Human brains are so good at finding patterns that we tend to see them even where they aren't. This is why statistical tests are useful and why the real-time statistics for random.org numbers are published online, transparent, open to the public, right? So this is what we're fighting back against, our tendency to see patterns in the noise when all there is noise. So I'm going to give you another good example of how we see patterns and see coincidences when we really have randomness. And this is where I'm going to ask you to do a little bit of a poll, all right? So I'm going to ask 2 questions, and can all of you raise your phones? I'm actually very impressed at the lack of phones and laptops. No, I mean, laptops are totally fine, by the way. But in general, there are usually more phones and laptops. So what we're going to do is a little bit of a quiz, okay? And the quiz goes a little bit something like this, right? So what is the probability that at least 2 people in this classroom share the same birthday? Right? So some of you may have seen this problem before. It's a classic statistics problem called the birthday problem. And it asks you to just sort of ballpark it, right? Given the number of people in the room, and I'd say there's about 100 or so, what's the probability that 2 people in this classroom share the same birthday? And then I'll ask you to be a little bit more specific, right? If we announce our birthdays one by one, how many do you think we'll announce before we find a shared birthday in the classroom? So I'm going to ask you, right? Over there, sure. Lija, oh, thank you for bringing your name card. No. Not yet, sorry. So we're going to ask you eventually, one of those days in October, like how we're going to ask you one by one, and we're going to see how many we announce until we find the same birthday. Okay, so first I want you to guess though, right? Because well, we'll see. how this works out. So why don't you go to this website? So I'm so sorry I jumped at you, Alicia. I was like, oh my goodness. It's okay. Again, it's okay to be wrong, especially when your professor overreacts. So if you all go to bit.ly/thingsquiz1, that should take you to a quiz. Let me know if that works for you. Okay, and I just want you to write in text, right, a number between 0 and 100. You can include decimals if you want to be super precise. And tell me what you think the probability is that at least 2 people in this classroom share the same birthday. Okay, and then, again, if we announce our birthdays one by one, how many do you think we'll announce? And so Lija is going to start, and then we'll go to Lindsay, and then on and on. How many do you think we'll announce before we find a shared birthday in the classroom? Yes, a clarifying question. Or a question.
Yeah.
Yes.
Is it that of the ones already said there will be a double, or as soon as one is said?
As soon as one is said,
right, okay.
right, it would be 1. Right? And if you think it'll take 2, you're just sort of placing a bet. Right? Do you think it'll be 2? Do you think it'll be 3? It'll be the third person? Would you be the second person? Would it be the first person? Okay, so now talk to the person next to you and argue about who's right and see if it changes your mind. That? All right, go ahead and submit. So I've got, oh wow, everyone's already in. So we got 108 responses. Let's see if we can get to 120. 120. I guess there are a lot of people. I'm so sorry. I hope it's not too uncomfortable. That's a really nice tool right there. It's kind of cushy. Okay. All right, so let's get to 120 and let's see what the responses look like. By the way, do you want to see something funny? And this does not reflect the typical computing practice here. So this is Stata, which is the program that we use in the statistics sequence. I was going to use this, but we don't need it. Okay, 124. Let's go ahead and see what the responses look like. So this is 95, 125, 5. You think we have a good range? Yeah. So this is what percent chance? What's the probability that you think at least 2 people in this class share the same birthday? So we have quite a range between 1. Do we have any hundreds? We have a few people saying 100. And let me see if I can get this. This is why I wanted to. Use Stata. Let's see if I can do summary. No, unfortunately I can't. Oh well, anyway, next time when I get Stata, I can actually put this in a nice histogram for you. But you can see that we have quite a range between 1 and 100. And then we say, if we announce our birthdays one by one, how many do you think we'll announce before we find a shared birthday? And if you say 1, and if you say a lot more than 1, right? Okay, so it's time, Lija.
Yes.
You ready?
Yes.
Okay, and after this, we're going to go to Lindsay. But I'm going to bet that someone's going to have your birthday.
Are you sure?
No. I can tell you exactly how unsure I am.
So, are you asking me my birthday?
Yes. I promise I will not snap at you this time.
My birthday is October the 16th.
There we go. Well done. Birthday buddies. Lija, what's your name? Jack Schultz, great. You should all go. So October, what was it? 16th. It's coming up. Yeah. Very good. Well, I look forward to wishing you both a happy birthday on October 16th. Lindsay, do you want to give it a try?
Sure. June 13th.
June 13th? No. Hillary?
June 8th.
Well, I'm actually surprised. June 8th, and then, I'm sorry?
March 24th. Cool.
March 24th? There we go. This is also a test of who's listening or not. So you can see, right, that this is very similar. This is clumping in action, right? The same kind of clumps, right, that we saw previously. And what was our reaction? Our reaction was like, oh my goodness, we won the lottery, right? Like, what are the chances? And the chances are quite high. They're essentially 100%. Right, that folks. So I will show you what this plot looks like. As long as you get over 23 people, the chances are even, right? Even odds, right? And as you get up to 40, it gets up to 80%. As you get up to 60, it basically gets to 100%, right? So in a class of 100, we are ceilinged out pretty much at 100%. It's almost guaranteed. Now, how do we, of course we can do a bunch of math, but how do we think of this like in terms of our intuition, right? And the way I like to think about it, right, is like imagine 365 balloons, right? And Li Jia throws a dart and pops one of the balloons, right? And now Lindsay throws a dart and has to miss that first dart, right? And she hits another balloon, right? And now Hillary has to throw a dart and hits a third balloon. That's not so hard. But after like 20 balloons, right? You have to miss the other 20, right? And then 21 and 21 and 22. You have to miss all the ones that are there, right? And as you get to like 80 or so balloons, right? What are the chances that every single time you throw a dart, you don't hit a balloon that's already been popped, right? So you have to start missing all of these all in a row, and it starts to become increasingly unlikely, right? So this is a probability that shows what's the probability that the first person will match? What's the probability that it will have to be the second? What's the probability it will have to be the third? So it's most likely that the first person. So I had about a 20% chance. Actually more, this is for 90 people, so I probably had a 30% chance of being right. So I got lucky on that one. So I really should buy a lottery ticket. But what's the point? How does this relate to the bombing and the clumping and the glowworms and the stars? We see patterns and coincidences, right, where truly there's randomness, right? It's just by chance. And you should do this at a big dinner party, right? Whenever there's like 30 people, be like, hey, I bet you. The two people here share the same birthday, and at 30, right, you're doing pretty well, about 3/4 chance, right, of winning that bet. Right? So it's a fun little game you can play. All right. So what's the point of all this, right? What is statistics, right? Why do we need statistics? We need it because our like enthusiasm over these random things but first of all, it's great. Right? First of all, it's kind of fun to have that, and we shouldn't push back against it. But if we're going to make high-stakes decisions based on our instincts, and our instincts are reliably wrong, right? We should have a set of tools, techniques, and practices to push back against that. And that's what statistics is. It's a set of tools, techniques, and practices that help us distinguish real patterns from randomness, right? Reality from hype, signal from noise. Right? And in a climate that we're currently in, needless to say, that is extremely important to have the discipline and the tools and the perspectives to know how to go to Stata or think with your friends about how to actually be able to tell if you've got a signal or if you've got noise, because we are really, really good at seeing patterns in the noise. Okay? So that's what is statistics. Let's get a little drier, and then we'll get a little more exciting. So now that you know what statistics is, like big S statistics, what is a statistic? Right? If someone tells you a statistic, this is sort of a pure definition. What is a statistic? So we have two general principles that we should establish from the get-go. The population and the sample. So the population is an abstraction to which we generalize. We generally consider it to be infinite. So imagine like the world, right? And so let's say we're trying to predict your height from your weight. And so this is a scatter plot loosely based on real parameters. Okay? So let's say that this is some infinite population, and even though it's not an infinite number at dots. This is for illustration. I'm showing you a lot of dots. Okay, and so what I'd like to do is say, okay, if I'm around 160 pounds or so, I want to predict my height, and then I might be a little bit taller than you might expect, right? And so this is that line of your prediction, and this is some people being a little bit taller than you'd expect for their weight, and this is some people being a little bit shorter than you expect from the weight. And so this is a population, and these are the facts about that population. Okay, so what we say is a parameter. This is a definition. A parameter is a fact about a population, but we never get populations in practice. Right? If we're doing a poll and we want to sample everybody in the United States, what we usually have to do is ask like 600 to 1,200 people what they think, and then infer from that what the population thinks. Right? And so in general, in practice, right, all the studies that we do as educational researchers are a small sample from a population to which we would like to generalize. Right? So the sample, right, looks like this, and in this case, I have a pretty paltry sample of 10 folks, right? And this is not, so already, like hopefully you'll leave here thinking, 10, not enough, right? Might have to get more. 10 is a pilot study. So, and you'll see why, right? So these are the data we've sampled. This is a finite size. In this case, I'm going to say n equals 10. N is our standard letter for sample size, okay? And so this is how we define a statistic. A statistic is a fact about a sample. And a parameter is a fact about a population. So a statistic is not inherently wrong. I mean, it's simply a fact about a sample. But it is wrong, in this case, right, if we want to infer from that sample statistic to what the population parameter is. Do you see what my best fit line is? Here is the population slope here in bold. And you can see my sample got it wrong, right? And in general, the samples will get things wrong. You just want it to sort of not be too wrong. And how do you get it to not be too wrong? Bigger and bigger samples, right? That's the intuition. So statistic, what is a statistic? It's a fact, but it's a fact about a sample. And usually what we care about are them facts about the population, okay? So like these facts about this line, that the intercept is here and the slope is there, are off here, right? And so what we can say then is that our statistics can be biased. So biased is actually a technical term. Right? We think of bias as a general concept here. Statistics can be biased. They can diverge from the parameter on average. And then they can also have variance. They can diverge from their average. And we're going to see that shortly. Right? And statistics can be biased with no variance. They can vary with no bias. Or they can be both biased and variable. And this one happens to vary with no bias. And I'll show you what that looks like. Right? So even though this is wrong, right, this slope here is wrong, on average it ends up being like this population slope. And that's a good thing. But you can see that it's going to vary a lot. And that may not be a good thing. So let's take a look at what this looks like. And again, here I'm hoping that you're starting to see what statistics is with new eyes. So here's my F9 resample. And what I'm going to do is up there, I'm going to sample 10 again and again from this population. And each time, I'm going to get a statistic. I'm going to get a statistic for the slope, which is how steep this is. And I'm going to get a statistic for the intercept, which shows you how high and low that is. And you can see, how would you describe that line?
Spastic.
Yeah, right. Yeah, it's flopping about, right? It's like it looks like a fish. And how would you describe this line? Is it flopping similarly? So it's a little more stable. We call that precision, right? It's a little less variable. Now, on average, do you see that even that line, as spastic as it is sort of centered on the true line? Sometimes it's going to go low. Sometimes it's going to go high. But on average, it's going to be right. Right? And this one, too, on average is going to be right, but it's a little less spastic. Right? And this is why we like big samples. Right? It's because, in general, they afford us more precision, a little less spastic. Right? Because this should scare all of us. Right? In any given study with a sample of 10, we might get a line that looks like that when the line we want is like that. Right? But again, statistics gives us a way to see just how variable that's going to be. Right? So that's two. What is a statistic? So again, what is statistics? It's a set of tools. What is a statistic? A statistic is a fact about a sample that could be wrong on average and also vary a ton. And statistics gives us a way to quantify that bias and quantify that variance. Okay, so that's number two. So what is statistics? What is a statistic? What I wanted to talk about here is a little bit about, again, because this is, when I give a course preview for S52, I say that this is a no, do, and be class, right? So we want you to leave knowing some things, We want you to leave being able to do something. This is what Liz City talked about in her talk today. Think about the tasks, right? Think about what it is that you can do. But I think, again, what I let off this morning saying is the most important thing I'd want you to leave this year, or again, this hour and a half feeling, is that I can be this, right? Like that quantitative statistical identity, right? Which you feel has always been like yes or no, math person, not math person. That's what I'd want you to leave most with, right? And so what does it feel like to do statistics? Oftentimes this is like what's in your head, right? It's like, yeah, so statistics is like you alone with a chalkboard writing Greek, right? And what I just wanted to be very clear about is that's not the way we do it here. Right, that's not it, right? So actually, this is the cover of Dan Koritz's book, Measuring Up. So I know that some of you are like, oh, should I go to Dan's or should I go to Dan's? One of my closest colleagues and friends, and was the mentor who hired me here. And so I should plug his book and his class, S11, which is absolutely fantastic. And so his book has some guy that looks maybe kind of like him, pounding his head on a chalkboard. But this is not the way we do statistics. I just have a few like Twitter posts so what does it feel like to do it? First of all, you're not alone. Right? You do this with your colleagues, right? And the whole reason we're having these turn-in talks is because that's what you're going to leave here with. You're going to leave here with a team of capable people who can do this stuff, and that feels great, right? And it means you're not alone, right? So this is similarly, this is from the Gutman Library. This is where a lot of folks camp out. So if you start to do some of this, right, or if you start to sort of take these concepts away, I don't want you to think of statistics as a solitary activity. It is fundamentally social and interactive, and you can see that, I guess, I mean, maybe Twitter is fundamentally social and interactive. Maybe that's dysfunctional too, but I also want to show like food, people cooking for each other, and ice cream. So which is how we get through statistical practice. And so this is what statistics looks like. It is social and it is fueled by ice cream. So I think it's important to say that, and I also think like it's important to think about how we learn statistics. And again, even if you never take S12 or S40 or S52 or S30, right? Even if you never take it, I want you to feel like you could get on that on-ramp and be able to learn this stuff in practice or in school in some way in the future, right? So in my experience, learning and teaching statistics, fluency comes only after repeated exposure to concepts in varying contexts. We call this layering. We think of this as like varnishing a piece of furniture, right? You need like, that's not social enough. It's like collaborative varnishing. Well, I'm not sure how to think of it. But that's the idea, right? Think about it like learning a language, and you cannot even learn a language like in 3 months, right? First, what does it take to learn a language? You got to be with each other, like other people, talking about things in an authentic, real way, right? And that's what it really takes to learn. And so I actually show this figure every year, and I update it every year. This is like my graph of what it feels like to learn S52 in S52. So here's like confidence with course material. over time, right? And it's this constant feeling of like, oh, like I have no idea what I'm doing. I totally get this. This is super easy. Oh wait, I have no idea what's going on. He just like talked for a week, and now I'm like leaving, and he's like speaking a foreign language, and then you slowly start to get it again. And so what I want you to do is like, again, regardless of whether you take the sequence or not, I want you to not be like held up by these roadblocks where you're like, oh, this Greek, and just keep exposing yourself with your colleagues, and it will come to you. I promise that. I promise you that. That's what we're here for, and that's what your colleagues should be there for in the real world. So be confident, immerse yourselves, help each other. That's what it feels like to learn statistics. Right? So what is statistics? What is a statistic? What does it feel like to learn statistics? Those are 3 of the most important things I want to leave you with. Okay? Onwards. What is a standard deviation? So this is like when everyone heads for the exits. One of the interview questions that we ask faculty members who come here and want to teach in the quantitative sequence, we ask like, tell me a concept that's hard to teach and why. Right? And in statistics, those of you who might remember, those of you who've never had it before, there's a day on central tendency. We call it mean, median, and mode. That's a nice alliteration. And that is one of the best days. Right? Everyone's like, oh, I kind of get it. I can see where the central tendency is. And the next day is usually standard deviations and variance. That is the worst day, especially by contrast. And so we always talk with like people who teach in the quantitative sequence about how do you teach variance. And so I've come to this. Actually, I remember when I was starting my master's program in statistics. It was my uncle who said, "Oh, you're doing a master's degree in stats. That's great. Can you tell me what a standard deviation is?" And I was like, like, I mean, how do you, it's one of those things that's like, what is education, right? Which is actually a useful thing to be able to answer. I just had no answer for it. And so that question, which I call the aunt or uncle question, right? Which is just someone in the street going, hey, you're a statistician. What's a standard deviation? And so what I thought of is like, this is like my 5 ways of answering that question, okay? And so in general, I'm going to start just with like general motivate, like why should we care about a standard deviation, right? In spite of the fact that I see it, sometimes for those of you who have like, I remember being in graduate school, I didn't have many investments, but I think I had like, from my teaching job, I had a little bit of like some TIA, CREF something, and it has like a standard deviation. I'm like, what is that, right? And so here are some questions that standard deviations help to answer, right? How much does educational achievement vary? Right, you heard me talk about this, for those of you who are at 8x8, you heard me talk about this this morning. How risky is my investment? Right? And so that's actually why my uncle is asking it. He saw it in his Schwab account or something like that, right? How certain am I? How confident am I? How precise am I? Right? Standard deviations help to answer that question. And what is like my margin of error, right? Like how, plus or minus how much, right? And that's what standard deviations, again, help to answer. So I think it's really important, even though this is the most frustrating day to teach. I'm going to try to do it in 10 minutes, and we'll see how it goes. So this is why. And so here are a couple of examples of how people communicate standard deviations in practice. If you've ever had like a freshman psych class, you might have done this. If I had more time, I'd do it. How many digits can you remember? Right, and so someone reads in a monotone like 7, and then 3, 2, and you just have to like, and after each one, you have to like try and write down as many as you can. Right? And so 7 plus or minus 2 is a standard answer for how many people can remember. But what does that mean? If like 2 is a standard deviation, like, and you get 13, what does that mean? Right? So that's what we're trying to answer today, right? Your child scores 2 standard deviations above the mean. So for those of you who got report cards, for those of you who are getting them now for your children or your nieces or your nephews, right? If sometimes they report things as standard deviation, you're like, what does that mean? Can you be more precise about what that actually means? The standard deviation of student achievement is 3 grade levels. That's something we learned from the data set that you might have seen this morning, and we cover in S52. Or the effect of a summer reading program is 0.1 standard deviations. And this is actually from Jimmy Kim's research, from our colleague here, Jamie Kim and Dave Quinn. So these are various ways in which standard deviations are used, again, like in business and in psychology and in report cards and in research, right? And so this is a concept that I think is absolutely essential that you have some grasp of, right, as you leave here. Okay, so what is standard deviation? What are my 5 ways of explaining a standard deviation? The first is graphical. Right? And actually, I'm going to make this physical in just a bit. So this is what a standard deviation looks like. And actually, I feel like one of the ways I can like test people on their statistical training is just like, can you draw me a normal distribution? And sometimes you get people doing like this upside down U, right? And so it's just like this gentle upsweep and this gentle downsweep. We'll talk more about this in a bit. So I've presented these normal distributions before. And when I have, I've used this little demo here. Right? Do you see those stick figures? And so that's what the normal distribution actually is saying there's more people in the center and there's fewer people in the extremes. And if you think about height and weight as that classic example, there are more people who are around 5'7", 5'8", 5'9", right? And fewer people who are 6'10" and 4'6", right? And that's the way that these distributions lie. And so then I'd go back to presenting the curves again, and people in my audience would be like, can you put the stick figures back, please? Like, I do not. This looks like it's going up and then it's going down. I don't get what that means. Can you put the stick figures back, please? And so that's what I think is really, so if you ever see these bell curves, think of the stick figures, because that's really what it's saying. There's more people in the middle and there's fewer people in the extremes. But that doesn't answer the question, what's a standard deviation? Right? The standard deviation, you have to sort of see there's a little inflection point. And what does that mean, inflection point? So here's where we're sort of going up, and here's where we're still going up, but we're starting to decelerate a little bit. Right, there's a little bit of an elbow, and I'm actually going to get you to stand up and do this in a bit, right? There's a little bit of an elbow right there, maybe like a shoulder or an elbow right there where it starts to pivot. And that's 1 standard deviation away. That distance here, from here to there, is 1 standard deviation away. And this distance from here to here is 1 standard deviation away. That inflection point is at plus or minus 1 standard deviation. Okay? So that is, as you look at this, you should hopefully be able to pick out which people, right, are within a standard deviation of the mean. Okay, and you can sort of see that inflection point maybe around there. So these people are over a standard deviation below. These people are over a standard deviation above. Okay, And so why is that important? Because we can actually quantify for distributions that look like this, we can actually quantify how many people are in there. Right? And so as it turns out, there's about 2/3, right, 68%, 68.2% of people within one standard deviation. Right? And so first I could have said to my uncle, right, it's like this distance right here. You see that? From my chest right to my elbow, right? That's the distance, right? And the second way I could have said it is there's about 2/3 of folks within one standard deviation. Plus one standard deviation, minus one standard deviation. So I want you to, seriously, I'm going to make you do this. I want to see how this looks, okay? So I want you to see like how my hands are shaped. It's not like this, right? It's a sort of gentle descent to 0. And see how I'm making this little crook in my elbow right here? That's what I'm going for, right? It's like it's going down, and then it's not going up, but it's sort of gently flattening out. And that's where this is happening, right? And it's sort of between the shoulder and the elbow. And so I'm serious. So, can you all stand up? So I want you to try to do this, and then I want you to critique your neighbor's bell curve. Right? So then I kind of want you to figure out where is your standard deviation? Like about where is it? And so find it on your neighbor. See if you can point it out on your neighbor. Where's your neighbor's standard deviation? A little wider. That's a little further out. Now put this down. There you go. Yeah. Hands down. There you go. All right. No, not. All right. So again, where is the standard deviation? It's not a point, right? The standard deviation is the distance from your elbow to your chest, right? It's that distance right there. That's plus one standard deviation, and that's minus one standard deviation. Okay. So if you're ever in doubt, I want you to sort of. So for those of you, is that what do they call this? Like proprio? I can't remember. But yeah. But some way that you can feel what a normal curve looks like, I think, is really important. Then we can start to do more variance, less variance, and kurtosis. And anyway, we'll get to the normal curve dances in S52. So again, within one standard deviation, you've got 2/3, and within two standard deviations, which is pretty much to your fingertips, right? I would say it's two standard deviations, pretty much to your fingertips. You've got 95%, right? And there are a few more where you can't quite reach, right? And that's the extra 5% outside two standard deviations, right? And so that's one way to think about what a standard deviation is. So if you want to get a little bit intimidating, this is the formula for standard deviations. Don't look. It's okay. We'll cover this later. We'll cover that later. But what is this actually? If I were to describe this formula, what I would say is it's an average distance from a point to the mean. Which is to say, if I had to pick a random person from this stick figure collection, how far would I expect, on average, them to be from the middle? Does that make sense? Right? So I mean, you're like, well, like some people are right in the middle, but some people are like way out here. So the question is, on average, how far away do you think that a person will be from the mean? And the answer is a standard deviation. Okay, so it's not quite the average distance. It's actually, if you want to be super specific, I should have put annoying here. Square root of the average squared deviation from the mean, which is the technical definition. But if you want to think about it, it's really more like how much do I expect a single person to be away from the mean, right? And that's the 7 plus or minus 2. If you think back to the psychology experiment, right? You're saying, I expect a random person to be like two digits away in that case, right? Which is to say that 11 isn't crazy, right? So intuitively, I want you to think of this. What I was hoping, I was actually on Amazon looking for big rubber bands, right? Because it's kind of like how stretched out you feel, right? The average amount of stretch. If I put each of you like as an observation and me in the middle, right? And like people were sort of, the further out you get, that's how big the standard deviation is, right? It's the amount of stretch that the spread out from the mean. And that's something I hope that you can feel as well. It's also a measure of risk, a measure of volatility, and that's where it comes from business, right? So standard deviations are like, ooh, how risky is that bet, right? Where do I expect this to be? Like remember that flopping fish of a slope that you saw, right? And then you can think of it as a margin of error, right? And this variation more broadly. So I hope with this you're getting a clearer sense of this, right? How many digits can you remember? 7 plus plus or minus 2. Okay, so how many people do you expect to be within 5 and 9? Yeah, 2/3, so around 68%, right? So 2/3 within one standard deviation. That's how you can think of it, right? Your child scores 2 standard deviations above the mean. What percentile does that make him or her? 95. It's actually 97, a little bit above that, because we're above the other 2 that are down there. But that's the idea, right? It's like that's pretty high. That's like 97th percentile, right? That's pretty high up there, right? The standard deviation of student achievement is 3 grade levels. But that's actually an incredible statement, right? Within any grade, like randomly picked from the United States, you have 3 grade levels of achievement and variation, right? So that's plus 1. That's plus 1 minus 1 standard deviation. Right? So that means there are people beyond that. Right? So even though I showed you, right, that there were districts that were really high and really low, that there's a lot of within grade, within school variation that we can't forget. Okay? And then the effective summer reading programs is 0.1 standard deviations. You're like, that's not that much. But we'll talk about how much that is relatively shortly. Okay, so I think it's really, really important to know just pure facts. What is a standard deviation? So when your aunt or when your uncle asks you that question, you're like, well, I didn't take the stat sequence, but I took this 90-minute thing, and I can kind of tell you that 2/3 are within. I can do this. It's this distance right here. So hopefully you can leave it that. All right, so that's what's a standard deviation. Now we're going to get super ambitious, and we're going to go for standard errors. Okay, so that was standard deviation, right? That's this. What's a standard error? Let's get into this. Okay, what I'm going to do is I'm going to show you like something really wild about statistics, right? Which is that again we can predict just how precise a statistic is going to be. All right, so here's this bell curve that I showed you before. I'm going to tell you its standard deviation is 5. Do you see how that's sort of going to the? You see that? Yeah. So it's like that's 5. Okay, and then what we're going to do is we're going to take a sample of 2 from this population. And then we're going to ask of this sample of 2, what's the average? Right? And what we're going to do is, well, the average of that and that is that. Does that make sense? It's like right in the middle. Right? Okay. And then we're going to say, okay, what if I had another 2? Right? What if I had these 2? Right? And I'm just going to, but like, wow, that was really, what were the chances of that? Right? And that happens from time to time. And so now we're going to take the average of that, and that's going to fall right there. And what I'm going to do is I'm going to keep taking the sample of 2, the sample of 2, the sample of 2. And then I'm going to ask again, what's the mean? What's the mean? What's the mean? Right? And then what you're going to see is that if you collect these means over and over from samples of 2, you're going to see something that looks like this, which is a little baby bell curve. Right? That's kind of cool. Right? So from this population distribution, I say, what would an average look like? And not just any average, an average of how many? 2. That's important. Remember that, right? An average of 2. Right? I can tell you what that distribution of averages looks like. Right? And it looks like a little baby bell curve. And in fact, I can tell you exactly how spread out that's going to be. It's the standard deviation divided by the square root of the sample size. So now watch this, right? What if instead of sampling 2, I sample 5? Or sorry, 16. 16 is more dramatic. If I sample 16 and I take averages, there's another little baby bell curve. What do you notice about this one? It's more precise, right? It's really, really tight, right around the true mean. And I can tell you, even beyond that, exactly how spread out that's going to be, because statistics is cool. Okay? So now let's take a look and see what this looks like in action. Because there's something I think about statistics where it has to be temporal in a way, right? You have to sort of see it over time to really get that notion of variance, right? So let's do this. Let's start off with sample of 2, and I'm going to animate it. There's 1, 2, and then there's the mean. Did you see that? Okay, here we go again. Here's 1, 2, and there's that mean. Here's 1, 2, and then there's that. And let's get a fun one. Wow, that's not that. Let's get 2. Let's. Oh, let's have that. No. I feel like. Oh, that's good. That's good. See how sometimes you can get 2 that are really far out. Let's go for. See, I'm not winning any lotteries here. So see, this is randomness in action, right? And so now what I'm going to do is I'm going to draw 5. That's 1. So I'm going to draw 5 and 5 and 5 and 5 and 5. You see what this button says? 10,000. So let's do 10,000 and another 10,000 and another 10,000, and another 10,000. And look, I'm getting a nice, beautiful bell curve, right? Where I know exactly how sort of shrunken in and precise it is compared to its parent, okay? So now let's animate what I showed you next, 16, right? So now this is going to be a long animation. Here we go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, really? All on that side? Oh, there we go. So do you see how that worked? Right? And so now I'm going to do 5 at a time. And I'm going to ask you, why is this tighter? Why is it more narrowly squished? Why don't I get one out here the way I did for n equals 2?
Because sample is more, and that represents the population of it.
Yeah, so what would you have to do to get something out here?
Radius, like spies, them that were over there.
Yeah, you need we're drawing 16 here. I mean, if I draw 2, yeah, I mean, I might get 2 out here. You saw that. But if I draw 16, it's really, really hard to keep drawing 16 from this side, right? So naturally, this is going to end up being more precise, right? So this, if I keep doing this, 10,000, 10,000, 10,000, yet again, I get a little baby bell curve, right? That I know exactly how spread out it is, right? Parent bell curve and baby bell curve determined by how big the sample is, right? The bigger the sample is, the more precise I get. And not just that, I know how precise that's going to be, and that's kind of cool, right? So my last demonstration is, if I want to make a really wacky looking demonstration, and so let's try this again. Well, anyway, the punchline is no matter how wacky the distribution, it still kind of looks like a baby bell curve. Not quite, but rapidly approaching. So that's really cool about statistics too, and this is why the normal curve is such an amazing thing. So no matter what that parent distribution looks like, as long as you've got a sufficiently big sample, you kind of know what that little baby bell curve looks like, and that's kind of cool. Now, why is that important, right? So here is the answer to the question, right? What's the standard error, right? This, whoops, let's go back to this again. This is the standard deviation. And then this, 10,000, 10,000, 10,000. This is another standard deviation, a particular kind of standard deviation. It's a standard deviation for a mean of 16. Right? And that special standard deviation for this statistic is called a standard error. A standard error is a specific kind of standard deviation for a statistic of a given sample size. And it depends on the sample size in a completely predictable way. So that I know, right, that from the same standard deviation populations with the same standard deviation, I can have a standard error for a mean of 2 that's a little bit bigger, and a standard deviation of a mean of 16 that's a little bit smaller, right? Okay. So that's a standard error. Why is that important? Because that tells you how precise your statistics are. And we know exactly what that is. There's actually a formula for it, and that's really useful. So this leads to some really, really important statistical intuition. 2 tenets that sort of sum up the first 5 of the 10 things that I think educational practitioners need to know about statistics, right? And the first is that the larger the sample I have, the more common rare observations and coincidences will become. Right, and that's what we saw, again, from the very, very first get-go, right? There are a lot of bombs falling. There are a lot of stars in the sky. There are a lot of coins being flipped. There are a lot of birthdays in the room. And the larger the sample you have, the more of these coincidences, right? Individual rare coincidences and observations, the more rare that will become. But another thing starts to happen, which is that the statistics that you might draw from these larger and larger sample sizes become substantially more precise, right? So that here's my illustration of this, right? Here's a sample of 1,000. Here's a sample of 1. So what I'm going to do yet again is, well, let's see if I can do this. I'm going to do yet again is some animation. And what's that circle? What are those circles? Those are the averages, right? And the average for 1, you see it's flopping around, right? What was the word you used? Spastic. That's my new word for imprecision, is spasticness. So that n equals 1 is flopping around, right? And n equals 10 is still flopping around. It's flopping around to a known degree, right? The standard error of that mean is still pretty large. But as you go to 20 to 50 to 100 to 500, the standard errors of these means become very, very small. And you do not see that circle jiggling very much at all. So these twin observations here, right? First, that when n equals 1,000, look, you're getting like these crazy observations. Do you see that? Right? If you have a big enough sample, crazy things are going to happen. And that's really important for you to remember, right? That when you have a sample, when you have like a big data like sample, like 400 million students that we had for our data set, you're going to see some crazy coincidences. And if you see something that's like 3 standard deviations from the mean, you're going to be like, all right, I have a lot of data. That happens. Right? These coincidences, when you have 100 people in the room and you're asking about birthdays, those coincidences happen. But what do I also know? I also know that statistics that I draw from these large samples will be very, very stable, very, very precise. So these are these twin observations that I think are very, very important. The larger the sample you have, the more common rare observations and coincidences become. This is like, again, statistical, the way you see the world. Right? And so, every day, if you're driving to school and you're like, oh my goodness, I just ran into my friend. What are the chances? The answer is, you're going to school every day. Eventually, you're going to run into your. So this is the way we have to think. It's like, okay, how big is this sample? Right? And yet, if I then take an average of all that, I'm going to be pretty sure about the likelihood that I'm going to see that friend. If I see that friend like 5 times in a year, I'm like, okay, next year I'm pretty sure that I'm going to see her, give or take 2 to 7 times. Right? And that's the standard error. Right? Okay, so this is the top 5, right? So what is statistics? What is a statistic? What does it feel like to learn statistics? What is a standard deviation? What is a standard error? This is lightning fast presentation. So if you're getting a little bit overwhelmed, don't worry. This is part of that ride. You remember? You're just in the trough, and don't worry, we'll push through it. We'll get you through it. And when you come back again, it's just like learning a vocabulary word in Spanish from like, that when you were like at that, after school workshop that my kids are in. And they're not going to remember it for like a year or so, but then they'll get repeated exposures, and hopefully it'll start to sink in, just like learning a language. Okay, so let's move on to number 6. The next ones are going to be a little bit faster given time, because we have a great barbecue for you coming up in half an hour. And oh shoot, I don't want to promise this. Do we know if there's an open bar? Yes. Okay. Sorry. I mean, not that I'm that enthusiastic about this. I'm actually going to show you some data about this shortly. So what is statistical significance versus practical significance? Another thing that I think is absolutely important for you to learn, because there are going to be these newspaper headlines that come at you saying statistically significant, and then I want you to be like, yeah, but, right? And then ask the important question, which is how big, how much? Okay. So statistical significance is we are sure the effect is not 0. Right? And we're sure to a certain degree. Right? If I say something is statistically significant, that means I know that the effect is not 0. So naturally, you should have a follow-up question, which is, how big is it? I'm really grateful that you told me it's not 0. But there is another range of answers that I'm interested in, and I'd like to know how big that effect is. Right? This is one of the most important questions that I think you can ask in any talk you see, in any article you read. Great, statistically significant, great, but how big is it? Right? Practical significance, the size of the effect. Is it substantial? Is it large? Is it small? What's tricky about effect sizes is what we call practical significance. What's tricky about them is they're sort of a judgment call. Right? Statistical significance are these sort of established benchmarks. Practical significance, not so much. So I'm going to give you a couple benchmarks I think are important for educational research. So this is an example of a statistically significant tiny effect. I'm sorry I didn't put the stick figures in, but you can imagine them there, right? So this is the estimate. It's in hundredths of an SD unit. So it's a pretty statistically significant. What I'm describing this as a tiny effect. It's like 0.02 standard deviation units, right? So if you're talking about like a summer reading program, let's say that moves at 0.02 standard deviation units. You can think about your bell curve. And you can think about this distance being 100. And you can think about moving 0.02 or 2 to 100. Right? So that's a statistically significant tiny effect. Okay? This is a statistically significant, and this is what I would describe as a modest effect. Right? So here you can see it's a little bit less precise. It's a little bit more spread out. But we also do know that it's centered on 0.06. Right? And that's what I would describe as a modest effect. So there are these guidelines that have been passed down from Jacob Cohen way back when. I would describe these as outdated and not applicable to educational research. These are outdated guidelines. I think it's important to know them because people still throw them about, but they, I think, are not useful when you're conducting educational research. So, and they're largely discredited for our work. So when you report differences between groups, a difference of 0.2 SD is small, 0.5 SD is medium, 0.8 SD is large. So you should know those, and then you should do that. Okay, so that's good to know. But here are, I think, the more established guidelines. What are better benchmarks for communicating the size of effects? It's always best to go to the most authoritative source, which is? Oh, Twitter, but Wikipedia is good. So this is Twitter, even more authoritative, I think. So this is Matt Barnum, who just won an award from AERA for education reporting, right? This is Stephen Sacha. I get really twitchy about studies that try to translate into weeks, months of learning. I do that myself, guilty as charged. And Matt Barnum, I think rightfully said, yeah, I'm not a big fan of the weeks of learning conversion. My very, very rough context-dependent rule of thumb for ed research effect sizes is 0.01 to 0.03, tiny, 0.04 to 0.09, small to modest, 0.1 to 0.19, moderate, 0.2 or greater, large. And I think that's right, and that's generally, if you talk to the quantitative faculty the quantitative folks in our faculty, they would largely agree. Okay, so when you see things reported in SD units, first of all, you know what an SD is. You're like, okay, I remember that little dance I was doing before. I can think of that as like 1, and then I can think of the movement of that, just control group, treatment group, right? That's like 0.2. Right? So you can see that that's not a very big effect, but normatively, like comparatively to educational interventions, it turns out, welcome to this field, it is extremely frustrating. It is hard to get large and sustained effects in education. And to a certain extent, you could think of that as all the different inputs, right, that happen in a kid's life, and also just how much we're fighting against when it comes to all of the experiences that they've had that may have been holding them back earlier in their lives, right? And the inequity of educational opportunity that we have in this country. So I think these are more established benchmarks that generally people go by, and I think, again, these are good benchmarks for you to know. So that's 6. So 5 and 6, this is statistical intuition in action. This paper just came out 2 days ago. Did you see this? Right? Maybe 3 days ago, maybe over the weekend, right? Weighted relative risk of alcohol for all attributable causes by standard drinks consumed per day, right? So what you see, and this is often how things are presented, you see these estimates, and then what's the shadow that you see? Yeah, that's not just any standard deviation, it's a standard error, right? It's the standard deviation of a particular statistic, right? And this is an estimated relative risk ratio. And just say what 1 is essentially no effect, right? There's no additional effect. And so what do you notice about this plot?
It's really big, really fast.
Yeah, whoa! Whoa, I mean, whoa. So yeah, I mean, there's a big standard error here. Yeah. What? Standard, I mean, I'm just speaking for myself, but like on standard drinks daily. I mean, this gets really high, really fast. What is going on, right? And so this is, of course, what people are noticing, right? So the headlines from this. Remember the headlines? How would you describe the headlines?
No one should drink anything.
Yes, right? So this is always what happens. So I would like you to leave here, again, with a little bit more skepticism when it comes to reporting and statistical research, right? And now you hopefully have a little bit more of a language to use with this, where you can say, okay, I can look at the magnitude of the effect, and I can also look at the standard errors. And what do I see for 1 drink a day? Which, right? One drink, I mean, that's indistinguishable from like 1 in this case, which is the same risk, right? A ratio of 1, right? And so this is again, authoritative source here. This is Twitter, right? Can someone please explain to me how a figure that shows that at 1 drink per day you have a relative risk of 1 can lead to the conclusion there's no safe level of alcohol consumption, right? And so this is a classic media reporting of a tool. While I'm at it, can we all agree that having a chart that spends 2/3 of its range above 5 drinks per day tells us more about alcoholism than light or moderate drinking? Yeah, I'd say so, right? And so these are the kinds of things like, and he keeps going, which of these sounds scarier drinking? So this is like dissection of statistics in a way that like I want you to think about this too, right? Like what would lead you to have the confidence to say, I'm going to think about this a little bit. Right? I'm going to actually like do some back of the envelope math of my own. I might like talk it over with a couple friends and say, does this sound right to you? And then like launch an opinion into the world. Right? And that's kind of what I want for you. I want a little bit of like reckless but also grounded confidence, right? That you can have an opinion about this, talked over with your team, right? And then launched into the world, which is when you submit every single assignment in this sequence and in your potential future positions, right? Because that's what this ultimately is. You, in your various capacities heading forward, are going to be making decisions based on quantitative data, whether you like it or not, right? Someone's going to give you this report from this journal. They're going to send you this newspaper article, and it's going to be along the lines of, should I have a drink or 5 tonight over at the banquet? And the answer might not be 5, but you also maybe shouldn't worry about having 1. Just don't drive, right? So that's the kind of like reasoning I want you not just to be able to like, oh yeah, I could probably do that, but feel confident in tossing out there into the world after vetting it maybe with a couple friends, okay? Statistical intuition in action. So number 7, we are moving along. Number 7, what is a correlation? This is a scatter plot that I showed you this morning. Maybe we might have to end on this because I want to leave a little bit of time for questions. What is a correlation? So do you remember what the correlation was on this? Do you remember what I said this morning? 0.8, right? And so what I would also like you to do, leaving here today, disciplined perception, right? Like a new way of seeing the world, where you look at the scatter plot and you're like, 0.7, 0.8, right? And some of you are like, what? And so what I want to do is briefly describe to you what a correlation is, because it's an extremely useful statistic. And when someone tells you it's correlated 0.3, 0.1, 0.9, I want you to have a vision of what that means. Okay? So what is a correlation, right? So I think one of the best ways to do this is just throw a bunch of pictures at you. Right? So this is a positive correlation, which is to say low on X predicts low on Y. This is no correlation, which is low on X, I don't know. If it's same as high on X, for all I can tell. Right? This is a more positive, or this is about the same negative correlation, which is to say low on X, high on Y. Right? And so you can see the tilting, right? Once it tilts past 0, then you can start to see it going in the other direction, right? And here's almost no correlation, and I say I'm putting this here because what do you see here? That's something pretty systematic going on, right? There's a pretty clear pattern here, and yet I tried to draw a line, and it told me there's no correlation, which is just to say that correlations are a measure of the strength of a linear relationship. And if there is no linear relationship, then you forgot to look at your scatter plot. So the first thing I'm going to encourage you to do is visualize your data. And part of what this sequence is all about is, again, seeing the data and then using numbers to explain it, only if those numbers truly do explain it. Because here the classic question would be, what does a scatter plot look like? And this is why you can see that Sean and I like to do these kinds of plots, because we like to see what the relationship actually looks like, and then we can start to describe it with a number like 0.8. Never jump to 0.8 without seeing the plot first, because you might make a mistake like this. Okay, so again, here's 0.65, 0.54, 0.39, 0.25, 0.18. And what you can sort of see here is that changing the axes makes it look different. See that? And so sometimes you kind of got to watch out, right, when it comes to like picking your axes and your ranges. Okay. So what I want to do, and maybe we'll just do this, and then I might have to close, leaving some of the best stuff for later. What I want to do is play a little game, and I forgot my prize. So unfortunately, there is a game called, has anyone heard it? Yeah. So I go to guess the correlation last night, and it says new game, and I'm like, all right, this is going to be so much fun, and then it's down. So everything's down, like state is down, guess the correlation is down. What am I going to do with my life? But there is another alternative. It's not quite as good, but it'll give you some good practice. So what it does is give you 4 to match, right? And we're going to start off a little bit slow. And I want you to say which one, so there's all 4 of these belong somewhere, right? So I want you to just write down right now, or just make sure you know in your head, right? Which one is 0.83, which one is 0.63, which one is 0.48, which one is negative 0.77. Okay? Give it a shot, compare with your neighbor over the next couple minutes. Again, it's okay to be wrong. There's a lot of people right now who are saying, I have no idea what I'm looking at. So help each other out. All right, so which one is the easiest to pick out? First one. Which one's that? Yeah, that's a negative relationship, right? Higher on X predicts lower on Y, so that's a negative one. Which one is this, do you think? Yeah, I think that's wait, what do we think that is? Yes. Yeah, is that right? Yes, yes. Is that? Yeah, that's right. Which one's this? That's 0.83 by process of elimination. 0.48. See, guess the correlation. I encourage you, once you figure, I shot him a Twitter note, and so I'm sure he'll get right on it. But hopefully that'll be fixed. Let's see how he did. So that's pretty happy. So unfortunately, we can't do the competition today because this is a little bit too easy, I think, for a group this size. But either Joe and S40, maybe Hadass and S12, or I and S52 will pick up this game with you, and we'll do a little competition if you join our stat sequence. So that's correlation. I'm going to do one slide on, it's just like getting to the good stuff and I have to stop. Why isn't correlation necessarily causation? Why can't we say, let's just give everyone more money? Not that more money might not necessarily help, but we should think about a policy to evaluate. But you've probably seen this before, and if you haven't, I'm going to spoil it here. Right? Well, and that's actually the way I'd like you to think, right? It's like, what would have happened otherwise, right? What would have been the counterfactual, right? So this is another classic by Tyler Vigen. This is like per capita cheese consumption correlates with the number of people who died by becoming tangled in their bed sheets. Well, that can't be right. 31 pounds? I guess so. Per year? Wow, that's and also, like, look at the number of deaths by stress. This is all actual data from the U.S. Department of Agriculture and Center for Disease Control and Prevention. Let me do a little bit of showing. This is Tyler Vigen. He actually has a book, so you're welcome to now a ridiculous book. U.S. spending on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. That's a little morbid. Number of people who drown by falling into a pool correlates with films Nicholas Cage. Right. So these are the kinds of spurious correlations that lead to the thesis for number 8, which is, of course, that correlation is not necessarily causation. So I'm going to have to flip through all of this. We've certainly covered this. So actually, does anyone know what this movie is?
Oh, sliding doors.
Yeah. Does anyone remember the? So what's the plot? I'm sorry, you're like, oh no.
I like the movie a lot. She basically, it's like if she got on the train, how her life would have been, and if she didn't get on the train, how her life would have been.
That's right, and that's what you want, right? If you want to do an experiment, you want to know what would have happened had that not happened, right? That's what we call counterfactual reasoning, right? And so if you're going to give a district some money, you also want to know what would have happened had you not done that, because if it gets better, it might have gotten better anyway, right? So you always have to say compared to what? You always have to say what would have happened had that not happened. And sliding doors, classic of, what is it, 90s? rom-com, I guess. A little bit morbid in the end, a spoiler alert. But in any case, the fundamental problem of causal inference is we can't find our twin from a parallel universe. But it turns out we have a lot of good ways of solving that I'm going to have to talk about some other time. There are, and many of which the point here is are covered by our excellent colleagues here at the School of Education, including Jimmy Kim, Eric Taylor, Bridget Terry Long, who is our dean, as you know, and one of the great economists in our field. This paper is actually, I think, in draft April 2017. So this is like, she just does not stop. She's just fantastic. And Eric Bettinger, one of her former students who is now out at Stanford. I wanted to just say that these are the, so number 10, probably most important. What can I do next? And then I'll open it up to a few questions and we can all go have one drink. So what can I do next? So I want to just briefly describe the sequence to you and then remind you that you don't have to take it. And I hope that you've left here with a few nuggets of wisdom to take on. But S12 and S30 is our foundational sequence. Hadass Edelman teaches this. She is absolutely fantastic. Our instructors in the fall sequence are stellar. I hate to let you down if you end up taking this with me because compared to Joe and Hadass, I struggle to keep up. S40 is our accelerated sequence. S12 and S30 are basically S40, but S40 goes at a much faster pace. And so they're going to have a lot of opportunities to ask and answer questions about this. What I would encourage you to do, and let me be absolutely plain here, like what I encourage you to do, and I would say particularly if you feel like you're not a math person, not a numbers person, our whole sequence is designed for you in particular, right? And not just you, all your friends, right? So like, because we do not do this alone. Right? And so that's how you gain strength in this, is by taking away this incredible group of also equally fluent, like quantitative folks who own an identity they never thought they could have. So I encourage you to stretch a little bit beyond your comfort zone, both by like not, if I wasn't going to take S12, maybe I'll take S12. I was going to take S12, maybe I'll take S40. I encourage you to stretch a little bit beyond your comfort zone because that's what we have designed the sequence to do, is support folks like you. Okay, so these are the two sequences. And I want to say too, like if you want to check them out, Tuesday at 12:30 is an optional math refresher for S12 and S40. You can meet, again, totally optional, but for people who, again, might feel a little bit nervous about it, that's what you can check out. Tuesday at 5 and 5:35, not the greatest times. There's the S40 class preview. Wednesday, there's the S12 class preview. And in case you missed the Tuesday math refresher, there's another, again, totally optional math refresher. Math is you can pick it up. We just want to make sure that if people have an additional anxiety about it, you're reassured right off the bat that that's not going to hold you up because, again, that's what we designed the sequence to do. But there's not just that, right? There are other courses of interest. My colleague Dan Koritz, who is, again, speaking just across the way somewhere, is absolutely excellent and is a legend in the assessment field, is teaching S11, educational testing. There's a fancier name for it. S10B is happening in the spring with Joe. These courses require S40 or S52, but I'm teaching a psychometrics seminar. This is usually for doctoral students and advanced master's students. And this is what you could look forward to in sort of a second year sequence. I should let you know that like all of my S52 grads, I give access to my psychometrics course remotely for. They can watch all the videos, they can do all the assignments. So this, like, once you're part of this family, you're always part of this family. You're just, as an alum, we want to think of you as just like lifelong students, lifelong learners. Think about that on, up and down road that you're on and ever forward, because if you got it wrong, then it means that you just haven't learned it yet. Right? And so we want to keep giving you this exposure and keep giving you these opportunities. And so with that, I thought I'll take the last 5 or 10 minutes or so, just open it up to general questions about these 10 things. We didn't get to talk too much about correlation and causation, counterfactual reasoning, but I'm happy to share my slides. I think this video will be posted somewhere, so I'm happy to review all of this. But let me first just thank you for showing up. It's getting a little warm in here, so let's, if you need to leave and go get a drink now, I totally get it. Or just some food, that's fine too. Let me be absolutely clear. But why don't I close here. Thank you very much, and let's open it up to questions. Yeah. What questions do you have? Yeah.
What's if the correlation is specifically for linear, then what's a nonlinear?
So you can model different nonlinear relationships. So you can actually see from the plot that I showed you today. Or earlier, both earlier today and right here. You can see that I've modeled a I've modeled a Gwyneth Paltrow, I guess. There you go. I have modeled a nonlinear relationship, and so we show you ways to do that. There are a bunch of different ways. The most common way is to do what we call polynomials. So you throw in x, you throw in x squared, you throw in x cubed, and you keep going as long as that adds information.
But you can't call it a correlation?
There are ways to describe the strength of the explanatory relationship using what we call an R squared, but that's not quite the same as a correlation. Yeah, but correlation is generally the strength of a linear relationship. Yes?
What seems to be like the gold standard in terms of like R, stata, in terms of Hugsy? Like,
so the standard tends to be stata. I should say, again, you're going to learn how to actually do this stuff in these courses, and so we encourage active software manipulation. So right now, stata is the default. Both Joe and I are endeavoring to offer bonus like R support, but your assignments will all be graded in stata in our sequences here. It tends to be what's used most often in educational and economic research right now. I'm a big fan of R. We're thinking about branching off sort of parallel stream in the future, but right now it's going to be stata only for the time being. I think that was you. Yes?
Yeah, so just back to effect size you've talked about, I'm wondering how do you reach the agreement to the new effect size? Because you crossed the former one.
I feel like I'm pretty authoritative when it comes to this, right? So this is a really good question, right? So statistics, like many fields, is a sort of consensus field. And when you say small, medium, and large, these are all judgment calls ultimately, right? And they have to be made in, these judgments have to be made in context. So even Cohen's guidelines, which I did a good job of sort of knocking here, in a fuller presentation that I give on the topic, I show that even when he presented his guidelines, he was like, no one should really pay attention to these because obviously it's context dependent. And of course, then everyone picked it up and was like, these are the authoritative guidelines. So I'm hoping I can do the same with Matt Barnum's Twitter feed. But I think purely normatively, like what are the biggest effect sizes we tend to see that are actually ultimately replicable? They're usually around 0.2 and 0.5 and 0.8. That's just, we never see effects like that. And if you ever do, I remember being in a presentation here and someone found an effect size of 1.5, and it was like a poor graduate student who was just getting grilled. And one of the comments was like, you should probably find some way to lower that effect size. Which is just to say it's like completely unrealistic. And so that's the kind of idea is that we just never see it. And so it's crazy to call something moderate when you never see something moderate, right? And you only see things that are small. And so it's just, I would describe it as a relative process and our growing understanding in general of how hard it is to have a sustained impact in education on average, which just shows how hard we all have to work together and how multifaceted our approach has to be. Other questions? Let's get a little more elementary. I feel like these are all sort of advanced. What about just like, I have no idea what this was or something?
Why is normal distribution normal? Why do you see it in many different situations?
Yeah, that's a cool question. There are a lot of ways to answer that. There's like a this is a good uncle question. Why is a normal distribution called normal? I might punt that to later. I actually just came from I have a lot of family out in San Francisco, and both at the Exploratorium in San Francisco and here at the Museum of Science for a long time, they had this it's like these balls drop. Have you seen that? And then they all filter down, and then it's like a little Plinko game, from the, what's that called, Price is Right? Yeah. And then, they all sort of fall down, and more fall in the middle, and fewer fall in the extremes, right? And it's probability, right? It's pure probability, and so you can describe the math of how that falls out and how that works out, and it's a beautiful distribution that describes the world well. There are a lot of distributions out there. This one happens to describe the world really well, and so this is sort of theory. Why is it useful? Because it describes the world. And that's kind of a cool thing, like the fact that I can make some wacky looking distribution and then draw a bunch of averages and it looks pretty normal is kind of cool. And that's why we can make the strong inferences we do a lot of the time using statistics. Yeah, good question. Yeah.
You asked for elementary, so here it is.
Yeah.
I went from I know what correlations are to what the heck, and then I'm back to what you say a correlation is the strength of a linear equation.
Linear relationship.
Linear relationship.
Yeah.
I don't.
Yeah. So I actually have a oh shoot, I don't think I brought my slider. I have a slider that shows one way to think about it is if I know X, how well can I predict Y? right? It's not quite right, but like think about it like that, right? So like if you go back to this correlation, these correlations over here, right? Oh boy, there's a lot of slides that we'll have to, right? It's like if I know socioeconomic status, right? Like if I know the average parent's socioeconomic status in a district, right? How well can I predict the average district achievement? Right? That's a useful question, right? So if this were a big blur and like low and high were both the same, it would kind of look flat or kind of look like a ball, right? And the tighter this is, the tighter that slope is, the more you can say, hey, if I know a district's socioeconomic status is low, I'm pretty sure it has low average achievement, right? And so the correlation is just a -1 to 1 number that says how strong is that relationship, with 0 being I can't say a thing, to 1 saying I can tell you exactly what it is. If you give me X, I'll tell you why. Right? And then 1 is positive relationship, -1 is a negative relationship where the higher the X, the lower the Y. But that's sort of how to think of it. So then if you go back to this nice contrasting cases here, right? You can see that, let's find one that's very strong, right? Right, you can see here, right, that if I know X, I'm pretty sure it's a pretty low Y, whereas if it's a high X, it's a pretty high Y, right? And that's why it's 0.8. It's sort of telling you, oh, that's a pretty strong relationship. Whereas here, if I have a low X, I have a medium Y, and if I have a high X, I still have a medium Y. So I can't tell what my Y is from my X, right? And so that's why the correlation is 0. So if you can think about it as like the ability to predict as well as this linear relationship.
And the bigger the sample, the more precise that prediction can.
So this is one of the big misconceptions that I try to address really on. This isn't quite what you asked, but I'm going to use it as a jumping off point. One of the big misconceptions people have is that the bigger the sample, the stronger the relationship. That's not quite right. The bigger the sample, what happens? Yeah, the more you know what that relationship really is, right? That's one way to think about it. So the more the sample size is, the more you have an understanding of what that correlation truly is. But that doesn't mean it's going to get bigger or smaller, right? So that's just to say, so the bigger the sample size, that does help you. What does it help you with? Precision, right? Where you have a sense that that line isn't going to waver so much. Right? That's really good. Yeah.
I was wondering if there's any support provided throughout the year that's comparable to like maybe the writing center or something. Let's say if we forgot to like integrate or differentiate or whatever, you just need a refresher.
I love the question. Let me repeat it for those of you on the side of the room. The question is, what kind of support network is there for the statistics sequence throughout the year? And then we're going to end on this question, and then we can all break for the barbecue. A ton, an absolute ton. So again, once you join the sequence, it is our job to get you through it and happy and content and confident. Just knowing enough to be dangerous is how we like it, right? So we have absolutely amazing, incredibly dedicated teaching. Say again? Don't do that. I have advice from previous advisees that they put on Post-its on the wall, and then one of them is do not take 5 courses signed. so that's not, I mean, some of you can do it, but in general, it's a good rule of thumb. A ton. Our teaching fellows are absolutely amazing and have just been proven through incredibly dedicated. And Joe and Hadass are going to, I mean, you're not going to see some, Joe and Hadass, they'll just like camp out in Gutman Library with like a giant coffee, and then you can just come up to them anytime. You should read their course evaluations. Like, don't read mine, but you can read theirs. They're truly remarkable and overwhelming. So I would say if you need extra help, ask for it. You don't need to go to a writing center or pay for a tutor. That's our job. That's what we're here for. Okay. With that, let's go enjoy the barbecue. Thank you all for coming.